Good morning, everybody. Today I'm going to do the video on related rates. And y'all, there's going to be a little bit of a change in the way I ask you guys to submit homework. It'll appear in your quiz section. It'll appear in your quiz section, and you'll just upload the file. Me asking you guys to take pictures and send emails is kind of clunky. There's a better way to do it. I just discovered it the other day, but it'll show up in your quizzes section. Okay, and I can make that a little bit clearer to you later on, but it's just the quizzes section on the left menu, and you'll upload any pictures you take. That way it'll be right there for me. I don't have to track it down via email. It's just a little more professional way of handling things. But anyway, thank you for your attention to that detail. Again, you'll be uploading your assignments rather than attaching them to an email. All right. Now, so folks, again, we're talking about related rates today, and it's a perfect description of what's going on here. Let me get organized here, folks. The topic is related rates. It means exactly what it says. And all the variables that we'll be dealing with will be functions of time. For example, the x variable is frequently associated with the horizontal axis, so we'll be thinking of x as a function of time. Okay, the y variable is also a function of time, and that's the vertical axis. You guys, these are all standard letters in math. Like we could be talking about something like volume. If you see the letter V, often that represents volume. That's going to be a function of time. All right, just anything, even angles, folks. An angle, the rate that an angle spins is a function of time. All right. So again, at the risk of being redundant here, any variable you see when you're doing a related rate problem is thought to be a function of time. And really, in life, that's everything is. Anything you know about temperature, pressure, heartbeat, all kinds of things. Everything depends on time. They change, and we're going to relate these rates that these various quantities change at. Now, the notation we could talk about if we were talking about the derivative, we could write this as x prime of t, right? I've actually seen people do that. I don't know why that didn't stick. That seems okay to me. And then you'd call this y prime of t, and so on, v prime of t. And you could call this theta prime of t. Now, it turns out the notation that's widely adopted when you're doing related rate problems is that the derivative is written in this Leibniz notation that I was discussing with you guys when we were face to face. So you can call it dx dt, dy dt, dv dt, all right, and then d theta dt. Now, you can use whatever notation you want, but this notation right here is kind of explicit. It literally says, how rapidly is x changing with respect to the time variable? How rapidly is y changing with respect to the time variable, and so on? Okay, and the weird thing about these related rate problems is you really don't even have to know the time explicitly, how many seconds have passed or anything like that. You can work this the notation is really lovely in terms of handling problems like this, and you rarely even have to know the exact time anything is happening. It'll ask the question, but that doesn't actually, the time itself doesn't enter into the computation, which is a little bit surprising. Okay, so again, y'all, this is just the notation. These are just notational considerations as far as what we're going to be doing for the next couple of days. All right, these notational conventions, I guess. Okay, now let's get to a problem here, and you can see this live. It's kind of interesting. These are clean problems, an interesting blend of calculus and algebra, as you've seen throughout the course. Proficiency in algebra always seems to rear its ugly head. Now, let's take a look at this one. I'm always double checking to see if this thing is focused for y'all. I had a little bit of trouble with that the other day in one of the other classes. Now, okay, let's read this one. It says, air is being pumped into a spherical balloon at a rate of 5 cubic centimeters. Now, y'all, that automatically indicates we're talking about volume, right? Right here you see the cubic centimeters. When you see cubic units, it's understood you're talking about volume. And of course, when you see square units, it's understood that you're talking about area. Okay. Now, sometimes just reading a problem and getting a feel for what the answer might be or what it's really asking is good before you get into the formality of the math. So this says determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. Now, y'all notice a key word here. They talk about radius, but then they play hardball here and talk about the diameter. So you got to pay attention to that. That can catch you if you're not careful. Now, here's where the notation is really just gorgeous. It says, what does it say right here? It says, determine the rate at which the radius of the balloon is increasing, right? What do you think we're trying to do here? We're trying to find dr dt, right? You see how the notation really, already you have a nice symbol that you're trying to find this value. You're trying to find the rate that the radius changes with respect to time, all right? Now it says, we're trying to find that. Now, what would be given right here? Okay, and again, y'all, I'm just reading the information. It's given that air is being pumped into the spherical balloon at a rate of 5 cubic centimeters per minute. All right, and so we're actually given that dV dt. You know, this is just a beautiful way to start any problem like this. Now, you don't really have to write the units down. They typically just cancel themselves. Some people like to write, you know, the units, but these type of problems, everything's always going to cancel in a nice sort of way anyway. And so I'm not going to turn this into a physics class where we're doing dimensional analysis. You know, you can leave this out, but it just works out if you set it up correctly that the units are going to cancel. And we'll be actually looking for linear units here. We're given volume units here. But we're trying to find linear units right here, the rate at which the radius is increasing when the diameter is 20 centimeters. Now also, by inference, we're also given that R is equal to 10 centimeters. And y'all see where that came from, right? They told us the diameter is 20, right? We all know the radius is half of the diameter. Okay, the radius is half of the diameter. So a good thing to do is write down everything you're given and see if you can fit it to something, then plug the numbers in when it's relevant. Okay. So we're trying to find the rate that the radius changes. We're given this information, and we're given this information by inference. Okay, half of 20 being 10. All right, now, so what's next? Well, we got to remember obscure formulas all of a sudden. And y'all, I will try to provide this for you. It turns out that the volume of a spherical balloon happens to be, and you actually prove this in calculus too. Some teachers do, some teachers don't. But it's 4/3 pi r cubed. Now there's one for surface area, I think, which is 4 pi r squared. Oops, sorry, are we on the screen? Yeah, good. Y'all, let me squeeze this down. I think I'm not going to screw up your viewing experience by doing this. Hopefully you can still see that okay. I think you're seeing exactly what I'm seeing. All right. Now, this is something I'll provide this for you. Like if you need some kind of relatively obscure formula that you may see once every year, even if you're a serious math student, you know, I'll give this to you. So this is the relationship between the volume of a sphere and its radius. And y'all, right up here, let me see if I can turn artiste on you. I'm going to try to represent three-dimensionality. There's a circle, right? So you can convey a volume, I think, by doing something like this. Sort of a smiley face there. And there's the center of your sphere, right? That kind of makes it look like a sphere or half of something. I don't know. But anyway, there's the center, and we're starting out, and the radius would be this right here, right? That would be your radius, R. Okay? Y'all, that is supposed to be a three-dimensional sphere. All right, trust me. Now, now here's where the calculus starts to kick in. If you differentiate this expression, you end up with dV dt. Right, folks? Very, very formal. You're differentiating this whole thing with respect to time. Now, the only thing that's alive right here, R is a variable, pi is a constant, right? So remember your chain rule process here. Bring the 3 around to the front. Remember, R is a function of time. And so by the chain rule, the 3 is going to come around and cancel with this 3 right here. And so you're going to end up with 4 pi r squared dr dt. Really, this is very much like implicit differentiation, except you have two separate variables. And when we were doing it earlier, it was just a function of x, right? And you just wrote down y prime. Some people wanted to do dy dx back then. It's the very same thing right here. You literally apply the chain rule. It may not quite look like it, but r is your inside function, right? So your outer function is the cubing function. You bring the 3 around to the front. This 3 cancels with that 3, leaving a 4 right there. You decrement this, and you get 2, and then dr dt by the chain rule. R is your inner function. It doesn't quite look like the chain rule, but it is the chain rule. All right. So what we have right here is an expression that relates. That's why they call this related rates. It relates the volume rate with the radius rate. Okay. Now, what were we trying to find? Now, way back, 3 or 4 minutes ago, we wrote this down. This is what we're trying to find. Okay, so before you plug any numbers in, isolate dr dt. All right, meaning you're going to write dv dt. And again, I would prefer you do this rather than try to substitute the numbers in immediately. It's a real hard habit to get used to. But dv dt is not really a fraction. It's just something that we know the value of right now, right? So you don't really have to think of it as a fraction. It looks like 1, but it's just a representation of it. So dv dt over, divided by this part right here, 4 pi r squared. I will say I do want to see that. I definitely want to see that. We were guided by this when we manipulated this, right? If we'd have been trying to find dv dt, we'd have already been done and we could just substitute the numbers in, right? Okay. Now, so dr dt is equal to this. Now, what we can do is we know that dv dt is 5. All right. And I'm going to leave the units out because they naturally cancel on a problem like this and it avoids a little bit of clutter. And then what's 4 pi r squared? Okay, that would be 4r is equal to 10, right? So is this r squared would be 100. So this would be 5 over 400 pi. Okay. Now again, you can verify yourself, but this does come out to centimeters per second. Okay, or centimeters per minute, excuse me. And I'm not going to go through, that's just kind of cumbersome, but the units naturally cancel for you. And again, you can verify that on your own, but I'm not going to hold you responsible for that. Now, also, this actually reduces also, again, in the name of space, I'll go ahead and do it for you, but we have 1 over 80 pi. And y'all, please leave your answer like that. That's totally fine. And the rates, again, are still centimeters per second. Centimeters per minute, sorry. Okay. All right, y'all, hopefully that's readable and you're comfortable with that. I didn't quite leave myself enough room on this handout to do this. I'm used to just doing it on the board. Yeah, spoiled me. I should have made this a little bit longer for you guys. But y'all, now, anyway, what is this about? It's a pretty slow rate of change, isn't it? Right? You see the volume is a lot bigger quantity, right? So the radius, but you can see that, I mean, that's kind of intuitive that the number would be small. I didn't know it would be this small. But y'all, that's approximately 1 over 240 centimeters per minute. Okay? So that's not much of you're not putting too much in per minute, really. A cubic centimeter isn't particularly big. You could do that in inches if you wanted to. But y'all, that is the answer. So we've done our first we've related the rate of the radius to the rate of the volume. All right, good. Now let's go on and take a look at this next one. Y'all, this next one's kind of a classic related. If y'all have ever sat to a calculus class, these ladder problems are kind of like the gold standard in terms of showing people something that's so-called practical application of related rates. Now, let's take a look here. All right, what we got going on here. All right, a 15-foot ladder is resting against a wall. The bottom is initially 10 feet from the wall and is being pushed toward the wall at a rate of 1/4 of a foot per second. How fast is the top of the ladder moving up the wall 12 seconds after we start pushing? Okay, it sounds complicated, but related rates turn into a pretty tractable problem. Now, let's just draw a general picture, folks, and see what's going on here. And the key on these, folks, is not to do too much, and you need to draw two pictures, which isn't taught in a lot of scenarios. There's two separate pictures, just a general picture where you set it up, and then a picture that actually corresponds to the particular point in time of interest. Now, I didn't draw much of a right triangle here, but we'll live with this. Okay. Now, so it says a 15-foot ladder is resting against the wall. So, okay, here's your 15-foot ladder, and that's constant. That's a constant length ladder, we hope. I wouldn't want to be on a ladder that was not a constant length. Maybe that would wake me up some mornings. 15-foot ladder right here resting against the wall. Now, what's your natural choice of letters here? You can pick the letters you want, but conventionally X is the horizontal variable, Y is the vertical variable, right? Pick whatever you want, but it's just kind of nice to stick with terra firma and the letters that we've adopted throughout time. All right, now, so that's the picture of the reality, all right? Now, we haven't really labeled it yet other than just with these general variables, but let's write down what we need to find. How fast is the top of the ladder moving up the wall? Okay, so we'll say, okay. And all this does make sense because you see this is being pushed in, right? That's exactly what it says. It's being pushed towards the wall. So if the ladder is being pushed towards the wall, it stands to reason that wait, is that what we're trying to find? Let's see. How fast is the top of the ladder? Yeah. So this would be the top of the ladder, right? So we're doing good here, folks. Again, if you're pushing the bottom of the ladder in, the top of the ladder is going to be going up, okay? How fast is the top of the ladder moving up the wall, okay? Now, so this would be the top of the ladder, right? And it's going to be moving. Now, so what do we got to write down in terms of our givens? Okay, the bottom is initially 10 feet away and it's being pushed towards the wall. So the X is a decreasing variable, right? X is a decreasing variable. So that means we're going to be given dx dt has to be negative. Y'all remember if a decreasing quantity has a negative derivative, right? Remember decreasing negative derivative, increasing positive derivative? That's what we're doing right here. So we're given that dx dt. And y'all, it is important to keep track of these conventions. Okay, so that's minus 1/4. And again, the units naturally cancel, so I don't expect you to write down the feet per second, all right? Sometimes you have to be careful because they may give you different units of time or whatnot, and then you have to watch out for conversions, which you can handle at the beginning of the problem usually. But right now, this is understood to be 1/4 foot per second. The minus sign is because X is a decreasing function, literally. All right. Now, so we're given this. How fast is the top of the ladder moving? So we're going to find, we have to find. And, I can't tell you. I used to not teach it this way. I would just kind of go willy-nilly and go, okay, what are we looking for here? This really is kind of a nice little roadmap for what you're doing. We're trying to find dy dt, right? How quickly that ladder is moving up the wall, right? So we're trying to find dy dt. Now, so what else? That's all we're really given other than this information. How fast is the top of the ladder moving up the wall 12 seconds after we start pushing? Now, we can get that written down now, or we could get that written down later. All right. It starts out 10 feet away, right? Okay, so it starts out 10 feet away. But how far would it move in 12 seconds? Well, wouldn't it move 3 feet, folks? Right, let's take a look here. The distance that the X variable would move, the distance would be equal to its rate, 1/4 of a foot. I'm just trying to time this to where I leave enough room. 1/4 of a foot per second times 12 seconds, right? Now, y'all can do this in your head, but I'm just showing you how the units cancel out. Okay, what does that equal? The 12s cancel out, the seconds cancel out. The 12 over 4 is 3, so that's 3 feet, right, folks? Now, not to insult anybody, but if you need to see that, that's useful. So you knew that ladder that was originally 10 feet away is actually moved 3 feet closer in. Okay? So what does that mean? That means you're going to have this picture. Y'all, in the name of clutter, I could actually draw two pictures right here, but this would end up being 7 feet right here. Okay. And this would be 15. Now, again, the labeling is not to scale as usual. It should be a much steeper looking thing, right? But y'all see where this 7 came from? It did start out 10 feet away, right? It started out 10 feet away, but in 12 seconds, it moved another 3 feet. So the 10 feet, now it's 7 feet, right? It would have been 10 feet, but after 12 seconds, it's 7. So this will be the actual diagram we'll be using when we actually try to put the numbers to this. Okay? So y'all, 2 separate diagrams. This diagram and this diagram. All right? This is just a general picture that describes the phenomenon of what's going on here. This is the actual snapshot in time that they're interested in. And here we used the 10 feet away in the 12 seconds. Right? So we have all our given information, everything nice and tidy. All right, now, back to the original diagram. A lot of these problems are Pythagoras Theorem or similar triangles. This is just Pythagoras Theorem. Right? Okay. Fair enough. Now, everything is understood to be a function of time. So when you differentiate with respect to time, you get 2x dx dt plus y squared dy dt. Now, I will personally track you down if you try to tell me this is equal to 30. Okay? It's tempting, you see the 2, bring it around, right? But y'all, this is a constant, right? A constant. It could be 15 raised to the population of the United States, which is rapidly declining. Bad joke, sorry. But 0, okay? 15 squared is a constant, so that's equal to 0, right? Okay. Now, let's go back, way back when. We're trying to find dy dt, right? So we have to just solve this for dy dt. You see, ladies and gentlemen, this really is clean if you just have the patience, to do it and not worry about that long reading assignment you have in history or English. Okay. Yeah. They're my friends over there. Don't worry. All right. So what we're going to do right here, folks, and I'm going to, since this is a calculus class and everybody's supposed to know how to do algebra, including me on a good day, we're going to solve this for dy dt. Now, y'all, I'm going to do it in one step here. Okay, dy dt. Okay. Now, equals to, I'm just going to take this whole object over to the other side, which is going to make it a minus 2x dx dt. Again, try not to be freaked out about these things. They look like fractions, but they're just things that take on values, right? As far as we're concerned. You don't have to worry about, is this a fraction? You got to do anything with it. All right. So now you're going to divide through by y squared. Everybody comfortable there? You guys are proficient, algebraically proficient calculus students, right? And everybody sees that. Did I make a mistake here? Am I? Let's see. I brought this over and I divided through by y squared, right? Y'all comfortable there? So right here, you already get 6 or 7 out of 10 just for writing that down. Now notice you should feel pretty warm here because we expect a plus answer. Well, this minus sign is going to cancel with this minus 1/4 when we put it in here, right? All right. Notice that this is our new x variable, right? This is our new x variable, so x will go right there. This x was obtained just by what we talked about earlier. Okay? So we know this. We know this. All we have to do is figure out what y squared is, right? Well, golly gee, if you come over here, you can do Pythagoras Theorem, and you get 7 squared plus y squared equals to 15 squared, right? All right, kids. So this is going to be equal to y squared. Y squared is equal to 225. They keep these numbers small enough where you can do it, I think. Minus 49, right? What did I do there? Brought that over, and where are we at here? Man, this is working out so well. I thought I was going to run out of space here. Okay, equals to 225, and then y'all, is this 176? Okay, My feeble mind just tried to do that in my head. I think so, because 176 and 49 is that number, right? Okay. So what do we know? We know that we don't care what y squared is equal to. We care what y is equal to. So y is equal to root 176. Okay. Now, y'all don't worry. This is not intermediate algebra. I don't expect you. You can leave it like that. Maybe you can simplify that down in an intermediate algebra class. Maybe it has a perfect square. But not interested in where square root of 176 is an okay number. It's a number between what? 9, 10, 11, 12, 13. It's a number between 13 and 14, right? 13 squared is 169, isn't it? 14 squared is 196. So this is a number somewhere between 13 and 14. Not important, though. All right, so, oh, God, we didn't have to know it, did we? Crap. Y'all, look here. We just need y squared over here, right? So all we have to do is write this down. Is minus 2 times, that was a waste of time. It was a waste of time. Time is precious. Minus 2 times 7 times minus 1/4, and that better be happening, right? These signs have to cancel because we're talking about a variable. Y is getting bigger, right? Y is getting bigger, so this better be positive or we've screwed something up somewhere. All right, y'all. Now, I'll leave it. You guys can do the arithmetic on that. I would give you full credit for this. Whatever. Well, okay. That's too unprofessional. All right. So let's. What do we got here? Okay, y'all. I'm just trying to do the simplification here. That would be 1/2. Just leave it like that. Okay, it's totally fine. Whatever that is, it's a positive number, and that's the rate. That's how rapidly that ladder is moving up the wall. Okay. All right, y'all. You have a good one. I've got to get some other videos done. Now, y'all, I will be posting a quiz in Canvas with a specific question for you. And again, I'll request that you upload that file in Canvas. It'll be, I'll try to put it in announcements or something, but you'll be going to quizzes. And again, I repeat, no more taking pictures. I'm the bad guy that got that bad habit started. But we're going to just do file uploads. It's much easier for you, and it's even easier for me because I don't have to track down all your emails. And that was a bad design thing on my part, but we live and learn, right? All right, folks. Only 13 reported cases of COVID here in Roswell, New Mexico. People are still going to places like Home Depot or getting takeout Mexican food at Burritos Express. You see some people walking in the park. Relatively tranquil here. It's not like we're in Manhattan or anywhere. But hope you're all doing well. Take care. Till next time.